guys, nice to see you. So last time we introduced um, rotational motion of rigid bodies. Anyone will give a definition of a rigid body?
And which also points out in the rotational motion.
Well, so it's not about how this body is moving. It's about the features of the body that it cannot be informed no matter what happens to this body. Any external forces for its motion does not cause deformation of the body, means change of its shape. And in other words, we can describe it as the points of the body do not change their relative position with respect to each other. So, from kinematic point of view, we have shown that we have direct analogies of linear velocity vector and linear acceleration vector, which is angular velocity vector and angular acceleration vector. This angular velocity vector, for instance, is a single vector which uniquely describes the rotation of the whole rigid body or any point of this rigid body. So we don't need to apply any other vectors. And the same stands for angular acceleration vector. If we look for some analogy between displacement and like for translational motion, and in rotational motion we have angle, actually, how much we rotate the rigid body, so it's equivalent of displacement. Also, in the scope of consideration of kinetic energy of rotational motion, we have shown that kinetic energy of rotational motion is defined as I times omega squared divided by 2. What is I?
It's inertia.
It's moment of inertia. And moment of inertia is a feature of the body, so shape, density distribution, and also what matters is the location, like position of the axis of rotation. So if we change axis of rotation, we need to calculate moment of inertia again. That's why every time when you provide some moment of inertia, it has to be specified with respect to which axis it was calculated. So we finished last discussion with an example how to calculate moment of inertia of a system of many bodies about different axes. Today we continue with an example how to calculate moment of inertia of a continuous body. So in that case, obviously we want to divide this continuous body in small fragments with small masses and then integrate it in order to get the moment of inertia with respect to some given axis. So let us consider this. In general, we can write that moment of inertia is equal to the sum for the product Ri squared times Mi. So that works well when we have a system of many bodies, and we have shown this previously. However, if we have a continuous body, a distributed body, then moment of inertia will be determined as limit of delta m approaches to 0. So we consider very small elements of this rigid body of this sum over all elements Ri squared times delta Mi. And in this case of a limit, we can substitute it with an integral of r squared times dm. So that's the equation which we can use to determine the moment of inertia of a continuous body. So now let us do it for one simple example. So let us consider some system of coordinates x, y, and maybe let us do it with a color. We have some rod, which is symmetrically oriented with respect to axis y. So we get the total length of this rod will be L, capital L. So coordinates of the left edge and right edge will be minus L over 2, and here will be L over 2. We consider that this rod possesses uniform linear density, which defined as lambda. And since it's uniform, we can express it as total mass of the rod divided by length of this rod. Now, obviously, since it's a continuous body, we want to divide it kind of to small elements with length dx. When we on the way to calculate moment of inertia of this rod with respect to the axis y. So let us write here I y will be equal, so let us write this general equation, r squared dm. So r here will be distance, like position of this small element with respect to origin of the coordinate along axis x. So that will be some coordinate x. So instead of r squared, we write here integral over x squared. Integral over x squared times dm. So instead of dm, we can write that dm is equal to lambda times dx. And instead of lambda, can substitute this expression. So it will be capital M over L and times dx. So now we can substitute it here instead of dm. So it will be M over L times dx. Also, we need to specify the range of integration. So we go from, so we need to integrate obviously for whole length of the rod. So we go from left edge at coordinate minus L over 2 to the right edge will be L over 2. So that will give us the following. We can take out the constants, integral minus L over 2 L over 2 x squared dx. That is M over L x cubed over 3, and this will be from minus L over 2 to L over 2. So here we can write M over 3L, and here we have L cubed over 8 minus, here will be negative L cubed over 8. So we end up here with M times L cubed. Let's write it like this, 3L, and here L cubed over 4. So L and cube we cancel out. Here will be second power, and we end up with M times L squared over 12. So that is the moment of inertia of this rod with respect to axis y. When we apply the concept for calculating this moment of inertia, assuming that we have a continuous body. What is important to mention here that it is always easy to calculate moment of inertia when we have some symmetry case. So in this case, we have symmetry with respect to axis y, and that is quite simple task. So that could be done also for some cylinder, some disc, whatever shape you want. If you manage to align your axis of rotation that way that there will be some symmetry, always quite easy to calculate it. However, that's not always the case. We obviously want to know how moment of inertia will be with respect to other points, which do not provide us any symmetry. And we need to calculate it every time for any new point. But that could be quite challenging when symmetry is absent. There is a nice so-called parallel axis theorem, which allows to calculate moment of inertia with respect to any points of the body when we know moment of inertia of this body with respect to its center of mass. So let us, in general, introduce it. So it's also valid for symmetric bodies or not symmetric, arbitrary shaped bodies. It's just the thing is it's more challenging to calculate the moment of inertia of the center of mass, like with respect to the axis which goes through the center of mass. But once we know already this for this given body, then doesn't matter where we move the axis in like parallel axis with respect to that one which goes through the center of mass, we will easily determine moment of inertia. So if we have some arbitrary shape rigid body, and let's say here we have somewhere center of mass, and we have an axis which goes perpendicularly to the plane of this screen through this center of mass. Let's say we know the moment of inertia with respect to this center of mass, ICM. Then we want to get value for moment of inertia with respect to some point P. And we don't want to calculate it definitely from scratch because it will take a lot of efforts. So here is some distance d between these 2 points, and there is, according to the theorem of parallel axis, we can determine moment of inertia with respect to point P as moment of inertia with respect to the center of mass plus total mass of the system of this continuous body times d squared. So with this, it's possible, once you know the moment of inertia with respect to the center of mass, you can get moment of inertia with respect to any point of this body, assuming that we have parallel axis of rotation. So it moves like this. If we move the angle, that of course doesn't work. So with this in mind, we can make a step forward and consider, yes?
Use parallel axis theorem.
So according to the theorem, the moment of inertia with respect to axis which goes through any point of the rigid body will be equal to moment of inertia with respect to the axis which goes through the center of mass plus the product between total mass of the body and square of the distance between center mass and this point. So what we need to know is moment of inertial center of mass. If we deal with some symmetric bodies, it's a really easy task to determine. Then once we know it, we can determine moment of inertia with respect to any other points. And from the name of these theorems, it's theorem for the parallel axis, and means that we need to consider the axis should move parallel to any point. If we change angle, then this theorem doesn't work. So it works only if we move this axis to another point, but don't change its orientation and keep it parallel to the initial one, which goes through the center of mass, which, with respect to which we already know the moment of inertia. So now, when we keep in mind this theorem for parallel axis theorem, let us move to rolling rigid objects. So we assume some surface, and here is whatever rigid body you like. It's either cylinder or some disk, doesn't matter. So here we have the center of this, or center of mass, we can name it center of mass. Then this one is the radius, and here let's say we have point 1, then it rotates and it moves to point 2. So what will be the length of this segment? Here, let's mark it with red. If the angle is theta. Then if we measure angle in radians, we can determine this length of the segment as the product of radius of this object times theta, angle in radians. So now, if we want to know the velocity of the center of mass of this rolling rigid object, that will be first derivative of this length s over time. And that will be radius times first derivative of theta over time. And this is radius times angular velocity. Obviously, that the same approach will be applicable for acceleration of the center of mass. So that will be first derivative of the velocity of the center of mass equal to radius times first derivative of angular velocity over time, and that is r times alpha, where alpha stands for angular acceleration. So now when we define how we can get the relationship between velocity and acceleration of the center of mass with such parameter as angular velocity and acceleration, we can proceed to consider 3 different types of motions. So first we have just rotational motion. This rigid body rotates about axis, which goes through the center of mass. So let's say it rotates clockwise. So in this case, if we consider these 3 points of our interest, there will be center of mass and these extreme points, the highest and lowest point. So here will be velocity vector, which is equal to omega times r. Here will be velocity vector, which is equal by magnitude also to omega times r, but opposite in direction. And what about center of mass? It will be 0 because axis of rotation goes through the center of mass. So that is pure rotational motion. Now let us consider what we have here when we have pure translational motion. So that will be, again, center of mass, V center of mass. And if we consider any other these extreme points, they will possess the same vectors in the same direction, because for translational motion, all points of this rigid body will move with the same linear velocity vectors. Now what happens when we combine these two motions together? We get the following picture. Center of mass. So this is velocity of the center of mass. Now if we consider this extreme point on top, that will be much larger, because velocity of this highest point will consist of two components. It will be translational motion plus rotational motion. That will be V center of mass plus R times omega. And we know that R times omega is equal to velocity of the center of mass for a rolling object. So that will be equal to 2 velocity of the center of mass. Now let us draw here this surface over which this rigid body is rotating. And what about this lowest point? Hmm? Can you repeat, please? There is no velocity with respect to the surface, because every moment of time, as this object is rolling, this point will be in contact with the surface. So if it's in contact with the surface, obviously with respect to the surface, it will be equal to 0. And from other point of view, you can tell, okay, we have translational motion velocity, and then we have also rotational motion velocity in this direction. So they kind of compensate each other, and that's why this point will have 0 velocity with respect to the ground. So we can write V equals to 0. So this point is quite important for us. Let us call it some point P. And now, at every moment of time, how could we represent a combination of rotational and translational motion with just rotational motion? So now we keep in mind that we have separate translational and rotational. We consider rotational motion with respect to the center of mass, and that's eventually the distribution what we get. But we can consider this rigid object to rotate about axis which goes through point P. At every moment of time, it will describe the combination of these both rotational and translational motion. So imagine that keep in mind here that this point P is not the same point, because as object is rolling, this point will change because new points will come. But we always, in every moment of time, consider that point of the rigid object which is in contact with the surface. So now, if we consider that some axis goes through this point P. And this object rotates about this axis. So velocity of this point P will be 0 because axis goes through it. Then we have velocity of the center of mass, V center of mass. We have distance here, which is radius of the disk. Now, if we consider the third point, which is at the distance 2 radius, velocity will be twice large. So actually, with such a model, we describe this system completely and correctly. So we can substitute combination of translational and rotational motion about axis which goes through the center of mass with just rotational moment which goes through this point about axis which goes through the point P. So now, what if we want to determine kinetic energy of this rolling rigid object? We know that kinetic energy of a rolling object, well, any rotating object, can be represented as moment of inertia times omega squared divided by 2. So now, if we substitute both translational and rotational motion about axis which goes through the center of mass with just rotational motion about axis which goes through point P, then we can write that kinetic energy will be equal not just some random moment of inertia, but moment of inertia with respect to this specific axis, which goes through point P times omega squared divided by 2. So now we have some symmetric object, that is disk or cylinder, whatever. It's quite easy to calculate moment of inertia of the center of mass. But when we want to calculate moment of inertia for this system with respect to point P, that already not symmetric case, and that could be quite challenging. So that's the moment when we want to apply this parallel axis theorem and take an advantage of it. So we can write that moment of inertia with respect to axis which goes through point P will be equal to moment of inertia of the center of mass plus total mass of this rolling rigid object multiply by the distance between these 2 points, and this distance is actually the radius. So here radius square. So that is our parallel axis theorem. Now, once we have already moment of inertia with respect to this point P, we can substitute it here in this equation for kinetic energy. So kinetic energy is equal to I center of mass plus total mass of the rigid object times r square times omega square and divided by 2. So now let us open this parenthesis. We will get I center of mass times omega square over 2 plus m capital M r square times omega square divided by 2. So what is this product? It's the velocity of the center of mass square. So we can represent it as I center of mass times omega square divided by 2 plus total mass of the rigid rolling rigid object times velocity of the center of mass square divided by 2. So we see here that we end up with two components of kinetic energy, rotational and translational motion, which of course has to be taken into account because otherwise you can misinterpret some conditions. So let us consider some example. We have an inclined plane some angle theta. And here is some rigid object which can roll down over this inclined plane. So what happens with this object in this point where it touches the surface of the inclined plane? We have some friction force between the object and the surface. And this friction force creates some torque, which we will consider a little bit later, but some driving force for rotating of this object with respect to the center of mass. So that will be the driving force to roll this rigid object down hills of this inclined plane. And we consider that there is no sliding between the surface of the rigid object and the surface of the inclined plane. So they are always in like one point in contact and it doesn't slide anywhere. So we don't lose anything. So the question will be, what is the velocity of the center of mass of this rolling object once it reaches the bottom of the inclined plane? So any suggestions how we approach this? So we definitely want to approach this with conservation of energy, so potential and kinetic. So here we have some height h. And obviously, since we don't have any sliding, we don't have dissipation of energy because of work done by friction force. So we can write that kinetic energy initial plus potential energy initial will be equal to kinetic energy final plus potential energy final. So what do we have here? Kinetic energy initial is 0 because it doesn't move at the start. Then we have potential energy, which will be mass of this rigid object times g times h. Then we end up with kinetic energy. Kinetic energy we already expressed. It will be given by this equation. So I center of mass times omega square divided by 2 plus m v center of mass square divided by 2. So we have it, and so keep it like this, plus 0 because there is no potential energy at the end. So our goal is to get the expression for the velocity of center of mass. However, in our equation, we can write it here. Total mass times g times h is equal to I center of mass omega square divided by 2 plus mv center of mass square divided by 2. In this equation, we have omega square, so we need to go from omega square to represent it in terms of v center of mass. So omega is equal to v center of mass over radius. So we keep this in mind. So with this, we can rewrite it capital M times GH equal to I center of mass times V center of mass square over 2 radius and plus mv center of mass square over 2. So now we can take out from the parentheses 1 over 2 times v center of mass square times I center of mass divided by r and plus m. So once we have this, we can express our unknown velocity of the center of mass. Will be r square. Wait, you are right. So we put here square and here square. Good, thanks. So we have a square root of 2 times m v center of mass square divided by I center of mass over r square plus capital M. So we can actually simplify it. We can take out from this parenthesis in the denominator m. So that will be square root of 2 times v center of mass square divided by I center of mass over r square m plus 1. So this will be the expression for the velocity of center of mass. And here we need to highlight one important thing. So again, keep in mind that
Why the velocity center was in the yes, not the actual. I think it should be mgh. Capital mgh. Because
yeah, okay, yeah, I wrote it not correct. Yeah, you are right. Somehow I was thinking too much about kinetic energy. So we have 2mgh, yes. And here 2, we get rid of mgh, we get rid of m, and that will be just gh. Correct? Okay, good. So keep in mind that we have distribution between the potential energy and two types of kinetic energies, rotational and translation. Now, if you imagine that instead of this rigid object which can roll down over this inclined plane, we have some block which can slide down through this inclined plane surface without any friction. And then there is a question, what will be the velocity of the center of mass once this block reaches the bottom of the inclined plane? And your suggestion, will it be larger or smaller than the velocity of the center of mass of this rolling object? Small. Smaller. Any explanation why?
Because some energy friction.
So we don't have friction loss. So this block slides over the inclined plane without any friction. So we don't dissipate energy because of performing some work with friction force. So in that case, will be the velocity of the center of mass larger or smaller than the velocity of the center of mass of this rolling object?
Smaller because it's the angle of it. And the first stage is spiral movement, and we take the second velocity of second mass will be always the sine, the cosine of the initial.
Well, but let's think about this in the scope of conservation of energy. So, what happens when we have a block? We slice without friction. We also have this block at the height h. It slides down, so its potential energy initial is mgh. Here will be 0. In this case, when we don't have friction, all potential energy will be converted to kinetic energy. So assuming that we have, of course, we keep in mind that the mass of the block and this rolling rigid object will be the same. So then all kinetic energy, potential energy, which will be the same for both cases, will be fully converted to kinetic energy. What happens with rolling object? We have to keep in mind that we initially have the same potential energy, but then we convert it in two types of kinetic energy. First one, rotational, and second, translational. That means that initially we converted all potential energy for the block to translational kinetic energy, which corresponds to velocity to the center of mass. In the second time, part of this potential energy went for just rotational kinetic energy, and only part actually resulted in the translational kinetic energy. Means that velocity of the center of mass of this rolling object will always be smaller than velocity of the center of mass of such a sliding block. Of course, without friction, otherwise that will be a different story. But that is a fundamental difference which you need to understand, that with rolling objects, you need to keep in mind that that is true. You can say that potential energy is converted to kinetic energy, but there are just two different types of kinetic energies which correspond to rotational and translational motion. That's why there will be a difference. So let us summarize our discussion today, and we continue the calculation of moment of inertia. In particular, we considered how to calculate moment of inertia of continuous bodies. In that case, we need to divide it in small pieces with very small masses and integrate all over the volume, surface, or length, depends which type of continuous body we have. And obviously, we operate with density, which is kilogram per cubic meter, like surface density, which is kilogram per square meter, and linear density, which is kilogram per meter. So we also discussed and introduced the parallel axis theorem, which helps us to determine moment of inertia with respect to arbitrary points if we know the moment of inertia with respect to the center of mass. Quite helpful, specifically for symmetrical objects, because it's quite easy to calculate moment of inertia with respect to the center of mass. And also we considered this kind of one of the most classical example of rotation of rigid bodies, um, in particular example of rolling rigid body, when we can combine translational and rotational motion and consider it together for specific rolling of a rigid body. So keep in mind, when we have rolling of a rigid body, we deal with kinetic energy of rotational and translational motion, which is important because if you don't do this and convert all potential energy into kinetic energy of translational motion, forgetting about rotation, that will lead to a wrong um, like result and misinterpretation of your initial set of data. So thank you very much for attention. We will continue on Friday with introduction of torque and angular momentum.